Okay, so I'll start, as always, by reminding what we are doing. So we learned some basic notions of information theory, which turned out to be just another name for statistical physics. And the basic notions are entropy, which is a measure of indeterminacy, but it's also the measure of information which you receive when you remove this indeterminacy. And then we learned that entropy is always a rate. It's something which shows how exponentially fast the number of realization grows, or with what rate you transfer information for a given set of objects. Then we learn a generalization as we generalized usual probability into conditional probability. Then we can generalize usual entropy into conditional entropy, and then we consider the difference between this. Namely, we had something, then we made a measurement, we received a message, we put some condition, and after this condition, our entropy decreased or unchanged. And this difference between original entropy and entropy that we obtain under condition we call mutual information, and it was a measure of correlation between what we obtain and what was sent, or what we measured and what is in reality, or what we perceive and what is out there. And then we realized on the next step that this mutual information is a particular case of an even more general quantity, which is relative entropy, which means that it's kind of, we have a true distribution and hypothetical distribution. And something that measures how different they are is a relative entropy. And these three quantities are very powerful instruments. So what we are doing in these lectures, including today's lecture, we are applying them to different things, or actually we're looking at different direction. And the moment you start looking using these lenses, you see something different. So when farmer says that he is mostly interested in matter, in how much grain or how much milk he will get, then we look at it and we say that, yes, but you do selection, and essentially what you do encoding. You encode the information about environment into genes of your grains or your cow, and this is actually what evolution is about. So it just changes your perspective on pretty familiar things. And last lecture was about life. We realized that essentially any living being, because it is in such improbable state, must all the time keep itself in this improbable state, and so must somehow throw entropy away, must maintain its state of lower entropy, which means that it consumes information. It must obtain energy from a more ordered state and generate it out into a less ordered state. It obtains matter. What we eat is a very ordered set of atoms, comparing with what comes out of us. It's a set of atoms which has much, much more entropy. And then we also discuss how such living beings process information. So there was maybe the first experimental insight that the way our eye, and not only our eye, the retina, on the first most basic level, on the first neurons which carry electrical signals, it actually encodes this optical signal according to its statistics. So it, in a sense, takes something which has some probability distribution like this and encode it into something which has a flat probability distribution. And if we pose any other condition, the flat distribution has a maximal entropy, which provides the maximal rate of information transfer from retina to the first neuron. And then we discussed highly speculative ideas and what actually is done with these signals as those signals go deeper into the brain. And I must admit that I love this theory of active inference and the way that our brain is always predict. I love it very much, and it explains to me a lot of things, both natural phenomena and society and myself. But it's highly speculative. I mean, I teach this not because this is, kind of stuff that Gibbs did 100 years ago, and we're pretty sure about it. So with this, take it with a grain of salt. But it's something which is really, at least the way that I learned it 30 years ago, it totally changed the perspective. So it tells you that it's not down-up process that you get some sensory perception, it goes into a brain, there it's encoded there or decoded, and then you get some idea of what is around. It seems that what actually happens is that our brain always sends signals out, predicting what kind of sensory signal he expects, and directs our sensory organs to get these signals. Then when he gets the signals, what actually sees is a difference. And he reacts on this difference, and there are two ways to react on the difference. Either change your generative model, change your perception, or change a signal that you get, look other way. But for me, one of the most powerful things that I remember that what convinced me is that we see object, we distinguish between three-dimensional object and a picture even with one eye. Like technically, we have two eyes to see three-dimensional objects because these two eyes see a little different picture. Our brain compares them, and they know the distance on which and he knows that this is three-dimensional world. But we also look at something, and if you're given a photo of it or the same object, the brain always knows what is the real object. And then you ask how it does it. And the brain actually predicts what happens if you move your head a little bit. Because when you move your head a little bit, this essentially you will see a little bit different when it's a three-dimensional object and the same when it's a photo, right? Even without moving the brain, he already predicts, maybe it is wrong, we could be wrong. So I think it's it's really very powerful new idea. You want to ask something?
I have a question, but might be a strange one, but what do you mean when you say prediction?
Prediction, I mean in a very physical sense. There are signals going out of the brain to the neurons which analyze signals coming from the eye. So there is some set of neurons which obtain signal from both directions. And they have different frequencies. We know which one is which. Okay?
I ask because let's say that my brain is built in such a way that it takes in information and the way it processes the processing mechanism itself is built on the assumption that the information is 3D. Is that a prediction, or is that just the structural way the data is processed, like an architectural prior?
Look, the brain, what we interpret in these terms, I mean, has nothing to do with what is there. What is there is electric signals. Some going in, some going out. Some which going in change something which is going out. Something which goes out change something which is going in. The rest are interpretations. What is important, and I think what is conceptually important because it's experimental fact, that there are as many signals going in, out, from comparing with out, in. And the signals which go out, they actually go before any sensory information appears. All the rest, interpretations. And they will definitely change in 10, 15, 20 years. Yes?
Well, the brain cannot figure out information that it doesn't have accurately, though. So if you look at things with one eye and it's something that like the eye cannot physically obtain information to tell whether it's something smaller but closer or larger but further away, then the brain kind of just guesses at that based on context. That would be.
Well, that's part of an experience. The most important part of it is to understand how brain actually comes into its present mode of operation. It's a bunch of neurons inside black box. What he gets are electrical signals with no labels attached. There is no label saying this is from your eye and this is from your ass. There's no such thing. So he gets the signals and sends something out. And then what he sends out, he can send signal to this, or he can send signal to something which you know, your motors, which control your legs, so you run away, or you listen more attentively. And as a result of this many things, he developed some kind of generative model. In terms of brain, generative model only relates signals to signals. He say, if I am sending such signals and obtaining back such and such signals, that means I survive. You're only interested in survival eventually, right? And then, okay, and I want to keep it this way. If I send these signals and do not obtain the signals which I obtained in the past, which is now part of my generative model, which is essentially conditional probability, then it changes its generative model, and it changes also action, namely the type of signals that he seeks. Okay? And what is really why I'm telling in this course, because it's a part of a thing which is called free energy. That's really and today will be also a lecture about the same things, how you actually find a balance. I think this is the mostly technically the most powerful idea which came out of physics, and of which now most of, you know, industry, engineering, finance, and everything else is an idea of free energy. And so today we'll have several examples which will continue to show you how powerfully it works. So today will be a general rate distortion theory, and then money. Information is money. Okay? So let's go forward. So first of all, we talk about what is pretty formally called rate distortion theory. Rate distortion theory. And this is something which is opposite in its formulation to what we did before. Before we were asking how much more information we can get, how we can increase the rate with which we obtain information. Now, after we obtain information, it's usually an opposite problem that we have, is how to encode it in a most compact way. Okay? So we'll be doing now with encoding. For example, if you're, so again, that will be B going to A, but let's say this B is a real number. And this B is digital, namely it has 2 in the power R, and this is a rate, okay? So it's just a binary signal, and so we can take it 4, 8, 32, but it always will be finite. Generally, to present a real number, you need an infinite number of digits, right? So now we say, okay, then we'll be distorting. Every time we present this B as this A, there will be some distortion. And we define it as a function which depends on A and on B. And it could be different functions, right? So simplest such function, and you will probably immediately tell me why, it's a quadratic function. So there is some A minus B squared, and this would be taken as an average, which means that I have some statistics of A and B. I take D of A and B, AI, Bj, AI, Bj, and I sum over all Ij. Okay? Why this quadratic is the simplest? We actually worked with it in our simplest approximation to the data, I don't know, when we were undergrads or maybe even in high school, is at least squared method, right? When we were working with least square method, we were minimizing this sum over all differences, right? So we're saying for this B, I have this A, but this is the real difference. Why we're doing it? Now we can understand it and interpret. Because if we are specifying only mean variance, it means that the statistics which has maximal entropy under this given variance is what statistics? Gaussian, of course. If you look for the maximum of entropy under given whatever, it's exponent of this whatever. if I ever want you to remember something technical from this course, is this. Maximum of entropy under condition R is exponent R with some factor, lambda, which you find out of normalization. Okay? So essentially, this distortion function corresponds to Gaussian statistics, and that's what makes it so simple. And because in the real world, we often deal with the sum of random numbers or sum of random factors or whatever, then we expect Gaussian statistics, and then it's natural to characterize distortion by a quadratic function, by variance, and try to minimize it. Now, if we have R equal to 1, which means that we have just two values, how much we can characterize B? What information about B we can give? If B is Gaussian, let's say. So probability of having B is 1 over square of pi sigma So I have this probability distribution, and I will represent it by two values of R, of A, because this is what I can have. What are these values must be if the what information I can convey? Huh?
You can split the distribution in half, so you could say positive and negative.
Yeah, usually one bit R equal to 1 means that you can divide your interval into two parts and tell in which part it is. That's it. Okay, that's what one bit is about. Because B changes from minus infinity to plus infinity, essentially it means that one bit encoding on a Gaussian signal, it's sign. So you just tell that it's sign. But it's more. Which means that for positive B, I take positive A, but I can take it 1, or I can take it 25, or I can relate it to this sigma, which is RMS value of B. It's B squared is sigma squared, right? So again, if I want to minimize this function, namely the integral over dB exponent minus B squared over 2 sigma squared sigma and A minus B squared. So I want to minimize it with respect to A. Apparently, I need to take A equal to RMS value of B, right? Which means that it's not that. So I encode the value of this is my B. So this would be my A, and this will be my A minus. So again, it's now not a dimensionless. My B has a dimensionality of sigma. So my A need to be in these units. Then this quantity or this integral will be minimal. Okay? But now, and the most interesting part of rate distortion theory, it's other way around. It's what is the rate, minimal rate. How minimal number of digits I can choose to present a given, to guarantee that my distortion is not larger than a given threshold. Okay? So again, I'm still working with this D. My D is a quadratic function. Okay? And now I am working with a signal B, which is Gaussian. So now I am asking the following question. For a given D, how much, what is the minimal rate which I can present that B with a distortion less than a given number D. This is given. This is given. Okay? Now I am asking about this. But what is the rate? What is the rate of information transfer from B to A? Again, everything is expressed in terms of three fundamental quantities that we use. So the answer of what is usually it's entropy, relative entropy, or mutual information. So what is the rate of information transfer of a B by A? Huh? Mutual information. Of course, this must be a mutual information. Well, we are looking for a minimum of a mutual information between A and B. Right? We know what is mutual information. We can write it in terms of entropy of B and entropy, conditional entropy. Right? So this is a minimum of S of B minus S of B under condition of A. Right? Now, when we are looking minimum, what are we changing? This or that or both? Because we are looking for encoding of A. Do we change S of B? No. It's given. It's a signal. What we are doing, we are looking for encoding. Namely, we are looking for some conditional probability of B under a given A, or conditional probability of A under a given B. Which means that because this is a given, that what we're actually looking for, we're looking for the maximum of S of B A, right? Now, what is S of B and A? It means that what is that you what is given to you is that A minus B squared is D. Okay? So you're asking what is the probability distribution has a maximal entropy under a given variance. So what is the probability distribution having maximal entropy with a given variance? The variance here is D. So what is this distribution? It's the second time today I'm asking this question, okay? So which probability distribution has maximal entropy at a given variance? Gaussian. Good. Let it sink in, okay? If variance is given, then the probability is exponent minus squared. That's Gaussian distribution. Okay, so what I can write then is the following thing, that this is a minimum S of B minus S of B minus A under condition of A. I could always treat it, but this is the Gaussian of B minus A. But I know the variance of B minus A. This is D. So I can say that this is already minimum, which means corresponding to maximum of it, will be the entropy of a Gaussian distribution over here, which is 1/2 log 2 pi E sigma squared. We derived the entropy of a Gaussian distribution, right? It's a logarithm of variance. And minus logarithm of the same, but now with a D. Okay? So this is the entropy of a Gaussian distribution with a variance equal to D, and this is the original entropy of a Gaussian distribution of B. And now I will see that this is equal to 1/2 logarithm sigma squared over D. Okay? So in particularly, when r is equal to 1, this is log 2. So d of 1, when I invert this formula, is sigma squared over 4, right? But generally, this is r of d. It's logarithmically depends on d, but the d of r apparently is sigma squared 2 minus what 2r, right? So that's what is called distortion function, either r of d or d of r. It tells you interesting things. First of all, when this turns to 0, this is it tells me that with this distortion you need this rate, okay? So for which dr is 0. I mean, I'm sure you know it, but for some reason you aren't participating. I mean, well, this logarithm is 0 when d equal to sigma squared, right? You know, I get used to Israeli students, which usually answer before I ask the question, and then I'm standing and waiting for the answer to when logarithm turns into 0. It's usually 1 point. The logarithm has 1, 0. Okay, so we see that when d is equal to sigma, the rate of information transfer is 0, and this rate is going to infinity when d going to 0, and it goes to infinity logarithmically. So when you want more and more and more precision here, then you need logarithmically more numbers, bits r. Okay? Thanks. Okay, so now when you vary, you will get a log. Let me use, I'll be using in the normal exponential form. So I would use a ln of p of bj over I divided by p of bj plus d. And when I write over here, this would be just a normalization factor, okay? D of A and B. So as usual, let me just put it in. What I obtain out of it is an exponent of my condition, okay? So this is, again, the same free energy or Laplace method, which tells you that whatever condition you put, you find it in the exponent. So your probability distribution of Bj under the condition of Ai is equal to with this factor, it's P of Bj unconditional, exponent minus beta d of A I Bj, and divided by z, which depends only on Ai and beta, which means it does not depend. So of course, z is the sum of, let me just write it here. So z is a sum over j, p of bj exponent minus d of Ai beta dAi bj. So this z is a function of Ai and beta. Okay? That's, again, a more or less straightforward realization of what we did. And it tells you how generally you solve and you find, and this is a very powerful technical tool to find encoding. This is encoding, okay? So for a given A, what kinds of B you expect. And this is a distribution generally, because you want to compress, right? For several, like in this example, you know, all these values of B represented by the single number. If we want more subdivisions, there will be more numbers, but still a big chunks of B will be presented by a given symbol A, right? So this is the whole probability distribution, and this is it. And it's given by the exponent of your distortion function. So whatever your both your nature or your machine requires for, I mean, what is the price of imprecision is determined by this function. So your encoding has this function in the exponent. And again, when you're a physicist and you look at it, and most of the people who do it, they're physicists, they naturally interpret it as a Gibbs distribution, with this being energy, right? And this being partition function. And then the question, and what is beta? Where it comes from? Okay, so I said we are looking for a maximal encoding, but then we add it for a physical system. We know what beta is. It's determined by environment. It's the temperature of a thermostat in which we are in. But you are designing a robot, right, or machine. And so what beta you take? How would you think about it? What is beta? What is the meaning of it? What is very, very low beta or very, very high beta? Let's start from very, very low. So your beta is very, very low, which means that in this part, this is really not that important. or in this probability distribution, this is almost a constant, right? So you don't much care for your distortion. What you care for the maximum of entropy. So you take your distribution as uniform as possible because you want a maximal entropy. It will be a little bit modulated by where this is large, because beta is small only when d is very large. Namely, only huge distortion will be taken into account. But most of distortion you won't care. Okay? So your beta is your device, is what actually you use, which gives how much value you give to the distortion. High beta means low temperature. As we all know, now minimum of energy are very important. At low temperature, system prefer to be in the minimum of energy. Again, I want to remind you that we are talking again about this. This T is 1 over beta. Right? So when T is very low, this is not important. The minimum of energy is important. The system really, it starts to get into ferromagnetic state because it's where minimum of energy is. So the same is here. And then it's a very interesting question which engineers, market strategists, I don't know, artificial intelligence people discovered relatively recently. It got very fascinating. It's what happens when you change beta. And we physicists know what happens when you change beta or temperature. What happens? What happens when we take a physical system in which always this competition between order and disorder, and when start changing temperature, and something dramatic happens. Not on all systems, but in most of systems, as long as there is interaction between parts, and this dramatic is phase transition. So now these people are very much fascinated that when they change this parameter, nothing dramatic happens. So you change this parameter, your encoding changes kind of smoothly, and then at some beta, a very small change of this parameter leads, for a large system, you need really big system, to a very dramatic change into your type of encoding, in the regime in which your machine works. Right? And this is really something which is suddenly took all these things that I remember when I was a student, and I had an engineering friends and biologists and other people, and they were used to joke at us at physicists and say, guys, you're interested in the events which has practically zero measure of happening. To observe the phase transition, a Curie point or whatever, you need to tune your temperature to a very, very tiny intervals. It's something which is non-generic, this phase transition. And now I look around and I see all these people, including biologists, very much fascinated by phase transition, but on this language, this is essentially a change, dramatic change, qualitative change, type of encoding. And in terms of, in a moment, we start off a little bit more practical and engineering problem, but it may change from like encoding something by 1,000 variables to encoding by 5. And now it's particularly in AI things, this is a very booming discipline in which they look, and they do it for living. They look at conditional maxima, but now they intentionally look for the phase transition which happens when you change this parameter. Okay, and maybe the last thing which I'll tell you before the break, and then we go to money business, is really how this works when, for example, you design self-driving car, right? So now what actually happens is that you have a third element here. Well, in a brain something similar happens, but we don't have a control of it. So you have a camera, it registers this information, and as you probably know, our eye gets like 10 to 5, 10 to 6 bits per second. And a good camera has as much. So it's a huge information which is just on your pixels, okay? But you have a processor. Oh, we all have a, well, it's not a processor. What is here? Definitely not a processor. It's something totally different. But a self-driving car has a processor. And this processor doesn't like working with 10 to 5 or to 6 bits. Neither, by the way, our neurons. So we want an encoding, C. So C is a code. So this is environment. This is signal. And this is encoding of this signal. Now, as usual, we want our encoding, namely mutual information between A and C, be minimal. We don't want all of it. And for visual information, it's totally evident, right? Most part of visual information is totally redundant. Why? Because all neighboring pixels are generally show you the same, right? As we discussed, the fly reacts only on a contrast between intensity, fly eye, right? But generally, we have a very complicated set of pixels, most of them showing the same. So definitely, we want to compress it as much as possible, right? Because there's definitely a lot of redundancy over there. But we want to keep something. And what it is, it's something that we want to keep. We don't want to hit another car, right? So we do care about environment, right? So we want our processor to still have something, and the better, the more, about the environment. So there is another mutual information which we actually want larger. And this is what? Yes, exactly. So there is I between C and B, because processor works with this. That's what you work with. So you now will be looking for encoding. Again, like here, you'll be looking for encoding, but you will be encoding this, right? So you get signal. You want to encode it into C, into a set of code words with which your processor would work and say, slow down, or safely accelerate, or turn right, or turn left. This is something which requires information about B, right? So you want C and B, and you want it max, right? That's what people get their $1 billion, and particularly our Israeli company Mobileye, which all made, I mean, the people who really got their 100 million, they're all theoretical physicists by training, well, all 4 of them. And that's the type of problems that they need to solve, okay? Now, this is much more non-trivial problem. Let's write it, how it actually looks like. So what you look is that you want this minimum and this maximum. So again, you make a functional. Let me write it in the symmetric way. CA, and this you want with a sign minus, because maximizing this would minimize the Horn filter. So you will be looking for a minimum of this minus I of CB times some beta. And I just want to keep it like this, so I want my beta to be positive, right? So this is more or less what is the functional that you want to minimize. And you will be minimizing it by looking for a type of encoding. And let's see how is that. It's called information bottleneck. The general idea, of course, was not invented by engineers, and was invented by university professors here in America and in Israel, and in collaboration. There is some, he already unfortunately deceased, the guy in Jerusalem and people in Princeton. But the idea why it's called information bottleneck, that you want to squeeze the information about environment through the kind of the more and more narrow bottleneck of codes which encode as little as possible. Okay, so but technically you are looking for the extremum of this functional. Let's see how it works. So I'll probably start here, and then I move. So far, it's clear what we are doing. Any question here? Okay, it's conceptually surprisingly not difficult, and technically, of course, it's very much involved. But at some point, it was also conceptually non-trivial. Just to realize that you're working with a Lagrange multiplier and a type of free energy minimization, this because engineers used to work with different approach, which is more like control theory, right? It's something which is kind of you indefinitely change behavior when you get some signals, and they were usually low-dimensional things. At this point, you're working at extremely high dimensions. Okay? This is a totally different game. Here, your main game is encoding. All this, dynamical control, etc., will come after you would kind of shrink it. Okay, good. So let's write it. So I C A minus beta I C B is equal. It's a sum over all ij. I'll write it like this. P of C, so first we'll work with this. C J A I P of A I. This is a joint distribution between A and C, right? I just, again, as I usually write a joint distribution as a product of conditional and original, and it's a logarithm P of C J A I divided by a probability of Cj. That's my first part. And my second part will be minus beta sum over jk, right? So j is my C, but k will be b. So it will be probability of bk Cj, probability of Cj, logarithm probability of p bk Cj divided by the probability of bk. Okay. So you have two terms. And now you are looking for what? We are looking for encoding. Yeah, that's what we are looking for. Okay. So we need to now vary it with respect to. But the point here is that it's now some other conditional probability over here. I mean, this is easy, right? This we already know how to write. We write it, we get log. We vary it, we get just a sum of a normalization integral. But we have this one. Okay? So we need to relate this to this. Of course, we assume that we know how this measurement works, right? Because we're now working with encoding. We're looking for encoding. We assume that we know this conditional probability. So now we need to relate this to this using this. And how it's done, let me write you the respective conditional. So this quantity which we are interested, well, we're interested in this, but we need to relate this to this. So what we do, we'll write that P of bk Cj equal to 1 over P of C. I'll write this formula, and then I ask you to interpret it. When you see a formula for some conditional probability and something on the right and something in the denominator, you immediately recognize this is as which formula? Somewhere we wrote it like this, for example. Sorry, I actually did it wrong. So probability of hypothesis under a given experiment is the original probability of hypothesis times a probability of this data under this hypothesis. This is a factor. What is this formula? You remember name? It's Bayes formula. It's 17th century. I mean, it's unbelievable how. So what is essentially written here is a Bayes formula, but it tells you that to get this conditional probability, you need this. And this is that you need to take every A. And for this every A, there is a probability to have B and the probability to have C. And you need to sum all these probabilities, right? And so essentially what is written here is a formula that the probability of B, K, and Cj is equal to this sum. Like in Bayes formula, this times this, it's a probability of H and A, and this is a probability of H and A, okay? So this is essentially how to get a joint probability of B's and C's. You need to sum over all A's through which they are connected by generally, I mean, there could be some of them could be zero, but generally they are non-zero. So now when you look into it, what you find out that it's not that easy to get your $1 billion for your startup, that you need to solve these two simultaneously, right? So you need to find extremum of this one, but what is standing here, it's also a linear combination, but it's a huge matrix, right? So this P of B, which is standing here, it's a non-trivial combination of this C of A's, right? This is known. This is your measurement. That's what wants here, right? This is something that you know how it works. You know how, if you have an approaching car, what image you will get on your camera. That you know, more or less. There's something which you already encoded, right? But now using this as a known coefficients, and again, everything is dynamic here, right? But at any given moment, you need to encode an image. So you're looking for this. So you're looking for this, which realizes extremum, minimum of this functional under this extra condition. It's an implicit problem. There is no such simple solution, right? Because generally, what was standing here in this case was this. Right? It was independent on this conditional probability, so it gets into the exponent. Now your condition, you remember that your condition is that you want to know something about environment. It also depends on your encoding according to this formula. So that's what usually there are different algorithms, and that's actually where people really work hard. There is a deep learning algorithm which an artificial intelligence algorithm which do it many times. You do iterative procedure, And when you do this iterative procedure, which means that you do series of encoding. You do C1, then you do C2, then you do C3, etc. Or you build layers of your processors. So you get this from camera, you get to the first layer of processor, to the second layer of processor. This is what is called deep. There are many layers between them. Technically, they are trivial. You do some kind of matrix, multiplication and all that stuff. But of course, you are interested in a kind of a right starting position and a right fast converging algorithm. And surprise, surprise, it's very much you're interested in what is this beta. How much this procedure, how fast it converges, how fast it works, it really very much determined by this beta. And of course, this is something which is, again, truly empirical. Okay, and this is more or less how this rate distortion theory works these days. And maybe one last remark is that there was pretty recently a surprising connection between what people who do this kind of a deep learning procedure, namely that you, and of course you also use a feedback when you do a learning, when you try to maximize this, you then compare it with what you really know from outside about your environment. But the surprising connection here would be that as you go from layer to layer, namely as you do kind of sequence, so this is something which is called index M, and this M runs 1, 2, many times, you look at evolving encodings, and this surprisingly has a connection to what people do in a theory of evolution, in its kind of theoretical biology, where they're interested in what kind of encodings and algorithms are evolvable, right? So that they really can change within their own class and bring you far away and not being kind of terminated in some kind of, and it's more mathematical discipline, I would say, but somehow it kind of make a bridge between kind of completely engineering problem of compressing information, keeping as much as possible, and a very theoretical problem of how actually the evolution could work on a, just imagine genetic code, how complicated. All living beings on this planet have the same code, right? Well, mitochondria has a little bit different, but it's essentially the same code. Imagine how it could evolve, like it was not that code, some kind of something else. How? It's a very non-trivial question, how such things, right? For example, we know now how languages evolve, right? But then again, as I said, alphabet was invented once, right? So it would be nice if we had different alphabets. They were invented by totally different, but no, they all evolved from one alphabet. Okay, good. So we can make a break now and come back like in 10 minutes. Or I can start the next chapter and we can have a break in 10 minutes, what you prefer. It's a kind of natural break between chapters, but it's a little bit less than half time. What do you prefer?
Today there's the pumpkin thing.
Pumpkin, yeah. So let's.
So if
we can go faster. So then I suggest we'll make 10-minute break now, okay? Or if you want 5-minute break. But, break is necessary. You need kind of, like when dogs come out of the water, you need kind of to forget everything I told you about rate distortion theory because we go now into money. So 10 minutes, 10? 10, okay. 10 minutes and we'll go into money. Good. And I'll